So now we're going to learn about matched samples or paired samples. And we have a little bit of an example here. And this example is we're going to have 6 workers. And we're going to measure what is the completion time for doing some process when they use method 1 versus when they use method 2. And so this is like called matched samples because here is one worker and we have matched samples for that one worker. And here's the second worker and we have matched samples. And it means matched, meaning for each worker, they're doing 2 samples, right? And both those samples are matched with that one worker. And this is also called paired samples. And it helps eliminate confounding variables. And so a confounding variable is a variable which messes up your statistics. It confounds your results. It makes them confusing. It makes you confused. It makes you confounded. And so like here's an example of like a confounding variable. So the workers could be a confounding variable. And so if we had 6 workers and then we had them all try method 1 and then we had 6 different workers and we had them try method 2, we could still get the completion time that a worker took to do method 1 and the completion times that workers took to do method 2, but we might no longer be measuring which method is the better method, the more efficient method. And what might be confounding our results, confusing our results, would be that like, you know, our first set of 6 workers, maybe they're really remedial and they were really slow and they're not that great. And so they took a long time doing method 1. And maybe our second set of 6 workers, they were amazing. And, you know, with method 2, they're just really smart. They're really on it. And so they get stuff done regardless of the method. But because it's the workers that were determining, you know, the completion times of method 1 and the completion times of method 2, that confounds what we're really trying to measure, which is like which method is the better method. And so by doing matched samples or paired samples, we have like one worker and we see how long does that take one worker to complete stuff doing method 1 and how long does it take that same worker to complete things doing method 2. So you also see matched samples or paired sampling with twin studies. So there are identical twins and identical twins have like exactly the same genetics, the exact same DNA. And because of that, you could apply a treatment to one twin and not to another. And you could really see the difference that occurs removing confounding variable differences in genetics. And so that would be another example. So here is a little description of confounding variables and paired testing and match sample design. So you can pause the video, you can read about it here, and then I'm going to scroll down. You can pause the video and you can read about it here, and then I'm going to scroll down and you can pause the video and you can read about it here, and then I'm going to scroll down and here's info about confounding variables. You can pause the video and you can read about it here, and then I'm going to scroll down and you can pause the video and you can read about it here, and now I'm going to scroll down and you can pause the video, you can read about it here. And then there's a little bit about twins because I just wanted to fact check that on myself before I shared it with you. All right, so yeah, we're going to do this. What's our question? Our question is right here. 2 production methods are tested under similar conditions. A random sample of 6 workers is used. Each worker provides a pair of data values, paired sampling, matched sampling, one for each production method. The test is conducted to determine if the mean completion times differ between the 2 methods. And so we find the difference here. The difference between 6 and 5.4 is 0.6. The difference between 5 and 5.2, this minus that is negative 0.2. And then when we add all these up and divide by 6, we get a mean of 0.3. So add them all up, divide by 6. We get a mean of 0.3. So the mean of their differences is 0.3. And we're going to see that here, right? Here's the formula for the mean. And this takes us back just to our normal formula stuff, which is this sheet right here. And I will put that over on the right. Boom, 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 boom. And put this one on the left. And so, right? Oh, no, that's not that sheet. We want this one. Where is it? Hey, now, did I close it? Here, let me open it back up. Downloads, and it's going to be like that one. There we go. And we'll put it over on the right. There we go. Put this one on the left. So actually, we don't have the formula for a mean, but that's it. You sum up all of something, divide by, like, sum up the number of data items, right? So the number of data items there are the differences. We sum all those up. And then we divide by the number of elements, 6, and we get 0.3. And then here's our standard deviation of this data. So take this stuff, figure out the standard deviation. It's going to be each data point minus the mean. And square it, sum those up, divide by n minus 1. That gives us our variance. And then take the square root of that, and that gives us our standard deviation. And so our standard deviation is that. And then we're calculating things here with a t-value. So we're using a t-statistic. And so I'm not sure if this is a new formula that was just given to us or if it's a formula that comes from before. At any rate, that's the formula for the t-statistic. And so when you calculate that, you get a t of 2.2. And I guess we're using a t because we don't know what our population standard deviation is. We're doing samples here, sample of 6 workers. And we're using our sample standard deviation right there. And then we're putting in the sample standard deviation right there. So maybe that's why we're doing the t statistic. So some of this stuff, you just take it on face value. Again, what we're learning here is we're learning different tools for different situations. And maybe one of the main things you're learning from this video is this idea of doing matched samples where we're getting 2 values for 2 different methods, 2 measurements, and matching those to 1 worker, or paired sampling, right? 1 worker has 2 pairs of results from 2 different methods, and those are paired with 1 worker. And so maybe that's one of the big things you're learning here. So our null hypothesis here is that the difference between the difference between the means, right? The mean of the differences. So the mean of the differences is going to be 0, and if it's 0, then there's no difference between the 2 methods. If the mean of these differences for the population, right? The population differences, if the mean of the populations for the differences. And again, here's our notation. So mu is the notation for the population mean, right? And so our hypothesis is that the population mean, the differences between the completion times is going to be 0, the mean of those. And so let UD, the mean of the difference in the values for the population of the workers. There it is right there. It said right there. So when we get this, and I'm going to open this up in one more window, and so it's this window here, boom. When we get all these things, we get a t of 2.2. We can draw out just a distribution. I don't actually know if this is a normal distribution with this data because, 1, we're using t, and t becomes way more suspect as to whether or not it's normal. You just know less about your population. And we also can apply the critical limit theorem. So critical limit theorem right here. Central limit theorem right here. And we can't apply that because we have less than 30. And you really need 30 or more. And if you have 30 or more, you could start to say, hey, this is approximating the normal distribution. You could pause the video. You could read about that right there. And you could also pause the video and you could read about it more. And you could also pause the video and read about it more right there. So because of that, I don't really know what this distribution looks like, but I just drew a bell curve anyhow. And so here I'm putting that the population mean of the differences is equal to 0, just kind of in the middle. And I get my t-statistic of 2.20. And so I just put that down here, 2.20. Well, actually, before I wrote that, I know that I'm doing this at a 95% confidence level, and it's a 2-tailed test because we're looking to see, if the differences are greater than or less than a certain amount. So if we're doing that, right, we could have really positive big differences or negative differences for our mean, right? Depending upon how these values came out, the mean could have been positive or negative. And so 2-tailed test, so we're testing each side, see if we went too far one direction or the other. And at 95% confidence level, we're going to have 2.5% alpha level of significance. The level of significance will be 5%, but and that's our alpha, and each tail will be half of that. So alpha divided by 2 is 2.5% in this tail, 2.5% in this tail. So 97.5% of our data is from here over to the left. And then we have 2.5% of our data from here to the right, right? Because this is 2.5%, it's 2.5%, which means if this is 2.5%, then from here over is 97.5%. So our probability there is 0.025 or 2.5%. And if we look, what is our degrees of freedom? So our degrees of freedom was 6. And this is the old way of measuring degrees of freedom. The original way that we learned is just one less than the number of elements in our sample. So we got 6 elements here, so our degrees of freedom are going to be 5. And I made that notation here, degrees of freedom are 5. And so with degrees of freedom of 5, I've got here, just as a reminder, here's our Z table, so you could reference it. I find it's useful to reference it. And then over here, here's our T table. That's what I call them. And with degrees of freedom of 5, that's 5 right there. And degrees of freedom of 5, and we have 0.025 right here, right? So 0.025. And degrees of freedom 5, 0.025 is right there. Degrees of freedom 5, 0.025 is right there, area in the upper tail. So 2.571 is our T value. And so at 0.025 with 5 degrees of freedom, we have 2.571 as our T value. This is like our critical test right here. And this is our test statistic right here. So we got 2.2 as our test statistic. And let me go find that other slide. That other slide is that one. There it is. So our test statistic is 2.2. And so that's right there. And at 2.2 and 5 degrees of freedom, let's bring that one up. 2.2 and, oh, it broke it apart. 5 degrees of freedom, there we go. Nope, that's too many degrees of freedom. Let's find one more. So we need this one. Where did it go? Oh, right there. There it is. All right, so 5 degrees of freedom. And we have, now I got to go back and look at that slide. This one. 5 degrees of freedom, 5 degrees of freedom, and we have a T of 2.2. Okay, 5 degrees of freedom and a T of 2.2. So our T score here, 2.2, is between 2.015 and 2.5. So our probability in the upper tail, right, the area in the upper tail is going to be between 0.05 and 0.025. So when we graph that out, right, we have the probability is 0.05 to 0.025, and our T is 2.2, which means our line's right here, and it's not over here. It's not in the reject area. So this is in the do not reject area. It's not like it went too far. There's too big of a difference, right, in the differences in the means, the sample means. So here, if we go back and we look at our data, well, I can look at it right here. Right, the differences between, okay, time for completion, differences in completion times, and then the mean of those differences. They weren't large enough to be out here in the reject the null hypothesis that, you know, the mean of the differences for the population are going to be equal to 0. If we went too far out here, we'd have to reject that. But because we're here, we could say the population mean of the differences between the completion times with 95% confidence is equal to 0 for all intents and purposes. And so that's what the probability, the p-value approach tells us. This is also what I think of it as either the t-value or the z-value approach, but you could also say the critical value approach. This is your critical value. This is your test statistic. That's what this tells us. It says do not reject the null hypothesis with 95% confidence. So that's right there. Statistics, I'm telling you, it's a little bit of a language and a mind game, and you have to learn to speak it and think it. So here's how the book presents that. And they do a thing where they double, you know, a value, and that's just a different way of going about it. But you can read through that and see if it makes sense. But they come to the same, to you, but they come to the same conclusion: we cannot reject the null hypothesis. So that's doing matched samples or paired sampling, and just that concept alone is one of the main things you're learning about in this video and this little part. All right, see you in the next video.